In this video, we will learn how to balance redox reactions using the half reaction method. So let's get started by analyzing this equation and trying to decide if the reaction is balanced as written. Go ahead and take a moment and try to figure this out. You may pause the video. Okay, let's go over this. So let's start by counting how many hydrogens we have on both sides of the equations, how many oxygens we have on both sides, and how many manganese we have. On the reactant side, we have 4 hydrogens, and on the product side, we also have 4 hydrogens. We have 1 manganese, and we have 2 times 2, which is 4 oxygen, plus 4 more oxygen, and so that's 8. And then we have on the product side 3 times 2 plus 2 times 1, and so that's 6 plus 2, which is also 8. And so we have the same amount of each element on both sides of the equation. But we are still not balanced. Why are we not balanced? Well, electrons are matter too. And on the reactant side of the equation, the sum of all the charges is -1. And over here, the sum of the charges is 2 positive plus 0 plus 0, and so now it's 2 positive. And so to go from a -1 to a 2 positive, you would lose 3 electrons. And so this reaction is not balanced as written. We need a different strategy in order to balance our redox reactions so that we ensure that our reaction is not only element count balanced, but also charge balanced. We have to make sure our reactions are charge balanced. And so to do that, we are going to be using a different strategy called the half reaction method. And so the first step of the half reaction method to balancing is to calculate your oxidation states of everything in order to identify what are the spectator ions and what is actually being oxidized and what's being reduced. So let's go ahead and work this out. So we have iron oxide, and oxygen is a 2- charge. And so I'm going to write that as a 2-. We have 3 oxygens, each of them are 2-, and so that's 6 negative overall, but each has an oxidation state of 2-. And now we have 2 iron atoms, and those have to add up to 6+, but we have 2 irons, and so each iron is going to be a 3+ oxidation state. Now we can go over to carbon. Carbon is a pure element, no charge. It's a solid. That is 0 oxidation state. Iron, similarly, no charge written. That's a 0 oxidation state. In carbon dioxide, each oxygen is 2-, and so 2 times -2 is -4. We have 1 carbon to counteract that, and so our carbon has to be a +4 oxidation state. Now let's look at what changed. Our oxygen stays 2- the whole time, and so oxygen is a spectator ion. Spectator ions just watch the reaction happening rather than actually participate. And so we're going to leave oxygen out of our half reactions. What is changing though? Iron is changing from iron 3+ to iron 0. And carbon is changing from carbon 0 to carbon 4+. So 3+ to 0 is going down, and so that's reduction. And then carbon 0 to carbon 4+ is going more positive, and so that's oxidation. So we can go ahead and write out our half reactions, and we'll just start by writing out the element on both sides with its charge specified, so that's 0 and 4+. And then we'll start off with our iron, going from iron 3+ to iron 0. All right, the next step is to add electrons. So I'm going to add electrons in a different color for our next step. And so if we look at this process here, carbon had to go from a 0 to a 4+, and so it had to lose 4 electrons. Now if we look at the sum of the charges on this side, the sum of the charges is 0, and the sum of the charges here is 0. And so both sides add up to the same thing. Oxidation is loss of electrons. Reduction is gain electrons. And so we're going to have our electrons on our reactant side. How many electrons? Well, we can look at the charge. The sum of the charges over here is 0. The sum of the charges over here right now is 3+. So we have to add our electrons to the reactant side so that we can make our two sides equal in charge. And so we have to add 3 electrons to our reactant side so that both sides add up to 0. The sides don't always have to add up to 0, they just have to add up to the same number. Okay, so let's rewrite our equations. We had carbon becoming carbon 4+ and 4 with 4 electrons lost, and we had iron 3+ gaining 3 electrons to become iron. Let's switch colors again. And now we have to remember that the number of electrons lost has to equal the number of electrons gained. And so we have 3 electrons being lost or 4 electrons being lost and 3 electrons being gained. Now we can't just change each one to like 3 or each one to 4. We have to make them equal by multiplying by a coefficient and distributing that coefficient out. So the lowest common multiple of 3 and 4 is 12. And so I can get to that lowest common multiple by multiplying the top equation by 3 and the bottom equation by 4. And so let's distribute that out like in math. And so that's 3 carbons goes to 3 carbon 4+ plus 12 electrons. And similarly on the denominator, we will have 4 iron 3+ plus 12 electrons goes to 4 irons. All right, and so now our number of electrons lost is equal to our number of electrons gained. Okay, and so now we can add those together. And so everything on the reactant side is going to stay on the reactant side. Everything on the product side is going to stay on the product side. I'm going to rewrite this a little bit more centered though. So everything on the reactant side, I'm going to write over here, 3 carbon plus 4 iron 3 plus 12 electrons. And now I have on my product side 3 carbon 4 plus 12 electrons plus 4 iron. Okay, and so now I look to see what can cancel out, and just my electrons can cancel out. And so I have my 3 carbon plus 4 iron 3 plus goes to 3 carbon 4 plus 4 irons. Okay, so now it's time to reform our compounds. And so we have to remember that on the reactant side, this was part of iron oxide. And iron oxide has the chemical formula Fe2O3. Since each Fe2O3 formula unit has 2 irons and we need 4 irons in this chemical formula, we're going to put a 2 coefficient up in front to ensure that we have 4 irons total. On the product side, this carbon was really part of carbon dioxide. Each carbon dioxide has one carbon, and so since we need 3 carbons to be balanced, we're going to put a 3 coefficient in front. This iron was a pure element, and so that one's going to be alone. And this carbon was a pure element, and so that's going to be alone. And so by maintaining this number of the atom counts that are in this line right here, we are ensuring that this chemical equation down here is also balanced. We can also add back in state symbols to finish off our equation. Okay. All right. So if you read the textbook has a longer procedure that involves balancing in acid and basic conditions, where you have to add water, H plus ions, OH minus ions. You are not going to be held accountable in Chem 3A for balancing in acidic conditions or in basic conditions. We will leave that for Chem 1A. On ALEX, you will get practice balancing simple single replacement reactions and simple combination reactions that do not require adding water or hydroxide ions. Let's do some practice problems similar to what you will encounter on ALEX. All right, so this practice problem is going to have us write the balanced half reactions for each of these reactions. You can go ahead and pause the video and try to work these out on your own before playing the video. Okay, let's go over this. So let's start by assigning oxidation states and then splitting this into half reactions. So our chromium starts off as a neutral compound, no charge written, so that's a 0 oxidation state. Oxygen is also a pure element, so that's a 0 oxidation state. Then they're combining to form an ionic compound where oxygen will be a 2- charge, and chromium has to balance out that 2 minus charge, and so chromium is going to be a 2 plus cation. So we have chromium becoming more positive, and so that's oxidation, and oxygen becoming more negative, which is reduction. And so my chromium is going to go in my oxidation line, and so that's chromium starting off with a 0 oxidation state, becoming chromium 2 plus. Okay, and so let's think about where our electrons need to be. This is oxidation, and so our electrons should be on the product side of the equation. And we can look at the charge. It goes from being a 0 charge to a 2 plus charge, and so that's going to need to lose 2 electrons. You can also think of it as the sum of the charges over here is 0, and so the charges over here need to add up to 0 as well. Electrons are negative, and so we always have to go to the lower of the two sides to make them equal. Oxygen starts off as O2 gas and then becomes O2 minus. Now we have to balance our atom counts first. This was part of a molecule, and so we're going to need to put a 2 coefficient there. We can't put a subscript 2 because in that ionic compound it will be separate ions. It's not a polyatomic oxygen in there. It would be separate ions in that ionic compound. So we put the 2 coefficient in front. All right, so now let's look at our charges. We have 0 over here right now, and then over here we have 4 negative. 2 times minus 2 is 4 negative. Now, when we add electrons to this half reaction, we have to go to the lower of the two numbers, which is 4 minus. And so I'm going to need to add 4 electrons to my reactant side of the equation. Now both sides add up to 4 minus. These 2 coefficients here, you might think maybe we should double everything in that chromium reaction, but for the half reactions you'll encounter on ALEX, they do want lowest whole number coefficients, and so if you have all even number coefficients, they would want you to simplify it. And so this is the lowest whole number that we can achieve. Okay, now for this next one. We have iron going, I'm going to change colors. Iron starts off as a 0 oxidation state. Chlorine is a 1 minus. 2 chlorines would be 2 minus, and so copper has to be a 2 plus. Each chlorine is a 1 minus, and then iron, it must be a 3 plus, because there's 3 chlorines, and then copper is a 0. And so chlorine must be a spectator ion. It's not changing, and so we can ignore it. We have copper changing, and we have iron changing. Iron is becoming more positive, and so that's a oxidation going from a 0 to an iron 3 plus. Now we have copper going from a copper 2 plus to a copper 0. And so we don't write the 0 charge. Sorry. Okay, so let's think about our electron placement. This is oxidation, and so our electrons will be on the product side, and we also have to make our sum of the two sides equal, the sum of the charges on both sides equal. Right now we have a 3 plus on this side is a 0, And so we can lower the side to meet that side by adding 3 electrons. Electrons will always bring it down. So we'll have to add 3 electrons. Over here, we have 2 positive. Over here, we have 0. We have to add our electrons to this side so that we bring our charge down to be 0 like the other side. And so our balanced half reactions are just written like this. That's all. Okay. So let's apply what we've learned to do another practice problem. Go ahead and pause the video and try to predict the products for this single displacement reaction, and also identify what's being oxidized, what is the oxidizing agent, and how many electrons are exchanged in this reaction. Okay, let's go over this. And so we know that, let's start by splitting this into ions so that we can predict our products. We have ClO minus, that's our hypochlorite ion. We had 2 hypochlorite ions, and so that's a 2 minus overall. And so our copper had to be a 2 plus. And then sodium is neutral, no charge. And so in our single displacement pattern, we have A, B, and C, and then sodium is going to kick out the copper because sodium will want to be a 1 plus cation. That's its common ion charge. And copper, so we'll have A bonded to C and then B by itself. And so we have to form a compound between our sodium and our chlorine. But it's really going to be between our sodium plus cation and our chlorine, hypochlorite ion. So we'll form NaClO because each ion is only a 1 plus. Now we need to have our copper by itself. Okay. And so we know that we need 2 hypochlorite ions, and so we can put a 2 coefficient there. And then we can double check our charge to make sure we're charge balanced. This adds up to 0. This adds up to 0. And so we are charge balanced. And so that's good. This one can be aqueous and this one can be solid. But the question asks us to balance the half reactions. And so we're going to need to write a half reaction for that change. We had copper going from being 2 plus to copper 0. And so we have our copper 2 plus becoming copper 0. It's not a plus sign, that's an arrow. And we have our sodium going from sodium 0 to sodium positive. Now I can add 1 electron to this product side for the sodium, and I can add 2 electrons to the reactant side of the equation for my reduction half reaction. And so what element is being oxidized? Well, our sodium is being oxidized. Sodium is being oxidized. What is the oxidizing agent? So we have to remember what oxidizing agents are. Oxidizing agents cause oxidation. Of something else. So since they cause oxidation of something else, that must be our copper hypochlorite, copper 2 hypochlorite, because that will cause the oxidation of the sodium. So we're going to write out our chemical formula, because oxidizing agents refer to the whole compound. Now it says how many electrons are exchanged in this reaction. So now we're going to go back into our half reactions, and we can see that we have 1 electron here and 2 electrons here. So we will need to make those electron counts equal by multiplying everything by 2. And so we have 2 electrons lost, 2 electrons gained, and so 2 electrons are being exchanged in this reaction.